For this video, another generalization or finding for a certain formula will allow us to tell the number of or the value of A, take note, sorry for that, is actually A sub R for distributing R identical objects into n distinct boxes. Now, take a note of this, that if we have A sub R, its partner would be the little coefficient x to the power of R, and we're going to solve for or find the appropriate partner of this at a certain process of using generated functions to tell us the formula intended for that. This is the task for this video, is to generalize that, so that later on we don't need to pass through those certain processes. We can use immediate this formula as long as we know that it's actually distributing R identical objects into n distinct boxes. Okay, this is actually similar to the idea of multiset because we have here R identical objects. So basically the objects are very identical, so we can say that it's a multiset but of one characteristic, and all of them, we have infinitely many, into distinct boxes here. So basically, so you would find later on that it's almost similar to generalized A sub R previously when we talk about the arrangement or selection of R objects, number of ways of selecting R objects into or in the multiset. So basically, we'll have the same output here, but of course, for this video, let's try to generalize that. Of course, if we talk about R identical objects, okay, and n distinct objects, boxes rather, there are n different possibilities of boxes, and you're going to place R objects. So say for example, if we talk about box 1, and by the way, we are using here the generated functions to determine the formula. What would be the appropriate, what do you call this one, generated functions for box 1, where we are going to place there R identical objects? Same thing, it can be chosen. It can be chosen once, it can be chosen twice, and so on and so forth. So we will have the same generated function here. That is also true for our box 2. Okay, we could also have 1 plus x squared plus so on and so forth. And since we have here a number of n distinct boxes, so for the nth box or box n, okay, so you will still have the same 1 plus x squared plus so on and so forth. So we are going to identify later on what is the A sub R that is paired for x to the power of R for our formula intended for this. But we are going to use here the condensed form for each of this, basically for all of that, because we have the same form. We can write that certain generated function by rational expression. You have here 1 over 1 minus x. Box 2 will also have 1 over 1 minus x. Until box n, you have 1 over 1 minus x. Okay? Looking at this string of 1 over 1 minus x, we know that they are of the same expressions, and there are actually n of them because we have until box n. So we can write it into one exponentiation. You have 1 over 1 minus x to the power of n. Okay? So once we do that, we can actually use the power law by distributing the exponent n to the numerator and denominator. And since the numerator is just 1, so regardless of what that n is, it should be equal to 1. And our denominator is 1 minus x to the power of n. Writing that using the law of negative exponent, we'll have your 1 minus x to the power of negative n. And this item has already a specific equivalent identity previously discussed in this playlist. That is actually just equal to this. Let me move down. 1 minus x to the power of negative n is just equal to the expansion of 1 plus n minus 1 combination 1 for our x, plus 2 plus n minus 1 combination 2 for our x squared, plus until you reach this form, r plus n minus 1 combination r for our x to the power of r. Again, this has already been described in the generalization for the generalized binomial theorem, and it works. So that's its equivalent, which are actually taken from these illustrations here. When you look into this, there is already x to the power of r, and that is actually the intended literal coefficient for our A sub r. So what would be our A sub r here? In short, this is our A sub r. Our A sub r is just r plus n minus 1 over r. Because that is again A sub r x to the power of r, the number of ways of selecting r objects is indicated by this coefficient. Hence, this coefficient. So if you're just looking at a certain problem and you can understand that it's R identical objects into n distinct boxes, you can just simply use this formula where R is stands for the number of objects you're going to select or take out from the set, n meaning the number of distinct boxes, and then you just simply take the combination using this illustration. Okay, that is for this specific item. Again, A sub R is equal to R plus n minus 1 combination R. Thank you very much for watching.